So now that we've got our rules for our series and parallel circuits squared away, then the next thing that I want to do, even though I told you I'm not big on math, I'm still not, but we're going to do a little bit of practice with doing some math on these circuits. And so we've got our victory over automotive repair, right? So we've got that down. And then we know that if I didn't know volts, then volts equals amperage times resistance. And then amperage equals voltage divided by resistance. And then resistance equals voltage divided by amperage. All right. So if we go in here and we start to calculate amps that are unknown. So if we didn't know amps, then our formula, if amps were unknown, is voltage divided by resistance. So if I took my 12 volts divided by 4 ohms, then that gives me 3 amps. If my ohms were unknown, then my formula is here, that if I knew volts and amps, then 12 volts divided by 2 amps would give me 6 ohms. If my voltage were unknown, then I would do my formula for amperage times resistance. So if I had 6 amps times 2 ohms, then that would give me 12 volts. All right, so 12 volts here. So then I'm going to go ahead and let you guys work on these others, and go ahead and pause the screen, finish these off on your own, and then we'll go ahead and review this. So spoiler alert, I'm going to move on and give you the answers on these, so I didn't want you to watch me suffer drawing this out, but we've got our calculations out here. Hopefully you guys got this. So this is where we left off. So if we had 12 volts divided by 3 ohms, that gives us 4 amps. If we didn't know the voltage, then we would be amps times resistance. So 3 amps times 6 ohms gives us 18 volts. If we didn't know ohms, then we divide by our amperage. So 48 volts divided by 12 amps gives us 4 ohms. Then if we didn't know the amperage, we divide by our resistance. So 48 volts divided by 6 ohms gives us 8 amps. Then if we didn't know the ohms, 24 volts divided by 6 amps gives us 4 ohms. If we didn't know voltage, then 3 amps times 4 ohms gives us 12 volts. So then moving on to the next one, this says calculate the current for the following and answer the question. So on here, this is now gonna be the same formula for each one of these. So we're going to use the same amperage equals voltage divided by resistance. So if I had 12 volts divided by 2 ohms, that gives me 6 amps. If I had 12 divided by 3 ohms, that gives me 4. If I had 12 divided by 4, that gives me 3. So as resistance increased, voltage remains constant, resistance increased. Amperage, as resistance goes up, amperage goes down. Then calculate the current for the following. So in this case, the resistance is staying the same and the voltage is what's changing. So in this case, 6 volts divided by 2 ohms gives us 3 amps. 12 divided by 2 gives us 6. 24 divided by 24 volts divided by 2 ohms gives us 12. So as the voltage increased, the current went up. So voltage is pressure. Higher the pressure you have, the more current it will push. So now this is a calculation for a circuit here that first off, is this a series or parallel circuit? So this is series. So this is going to be a series circuit. And so to calculate the total resistance of a 2-volt series, you first have to add the resistances up. So if we call this resistance 1 and this resistance 2, then we're going to add those up. So we're going to say for this one that we're going to go 2 ohms plus another 2 ohms. That's a 2, I promise. And that would give me a total of 4 ohms. So now that I know the total resistance of this circuit and understand that this is going to connect back to here to complete that circuit back to the battery. And so this little upside down Christmas tree is a representation of ground. But now that I know the total resistance, now I can calculate the amperage. So if I go 12 volts, like it says, divided by 4 ohms, that gives me 3 amps. So this would be 3 amps. Now for this one, 2 ohms plus 4 ohms gives me 6 ohms. So if I add those up for my series circuit, because your total resistance is the sum of all the individual resistances, then in this case, we're going to then have 12 volts divided by, and this is volts, divided by 6 ohms, and that will give me 2 amps. Good enough. So this is now a different calculation. Is this a series or a parallel circuit? So this one is now parallel, but I've got power going to this bulb in its own ground, and then I've got power going to this one in its own ground. So to calculate parallel circuits, I want to give you a really simple formula. There's more complicated ones, but I don't see a lot of value in it. And so the really simple formula that we're going to use is R1 times R2 divided by R1 plus R2. All right. So that will give us our resistance total. Resistance total. So if I call this one R1 and this one R2, then we can say that our formula for this is going to be 2 ohms times 2 ohms. There's our omega symbol, believe me. Then 2 ohms plus 2 ohms. So this 2 times 2 gives us 4 divided by 2 plus 2, which also gives us 4. And so 4 over 4 means that our resistance total equals 1 ohm. Now, that also holds true with the formula with our rules for a parallel circuit, right? Is that the total resistance of these combined is less than any one of the individual resistances, which is mainly why I show the math. And so in this regard, then if we're going to calculate the amps, then 12 volts divided by 1 ohm gives me 12 amps. So this would be 12 amps there. Now, this one we could do the same way, but I'm going to show you another way that also illustrates one of the rules for our parallel circuit. And you can double check me with this formula over here later. But what is the voltage available here? So I've got 12 volts from the battery, and so for a parallel circuit, I also have 12 volts here, and I also have 12 volts here. So I can use simple Ohm's law and calculate the amperage for this leg and the amperage for this leg. And so if I call this again resistance 1 and that resistance 2, then for 1 we can say that we're going to calculate our amperage there, that I can say that I've got 12 volts divided by 2 ohms, and that would give me 6 amps. So I've got 6 amps for this leg. Then if I do the same for this one, for resistor 2, then I could say I've got 12 volts divided by 4 ohms. And then that gives me 3 amps. So then my total amperage would be the amperage of this leg plus the amperage of this one, which is 3 amps. So 3 amps plus 6 amps gives me 9 amps. The other part that I want you to realize is that this one has higher resistance down this circuit with this bulb, has 4 ohms, and so less amperage is flowing there. This one has lower resistance at 2 ohms, and so more amperage is flowing there. But the combined amperage through this section and then back to the battery over here, and what's leaving the battery here, will be the 9 amps total for both of those legs. 9 amps there, 9 amps here. All right. So 9 amps total here. All right. So now we've got one last exercise to do. So this is a series circuit, and the directions for this say answer each of the questions with one of the following statements that would identify the result of the problem. Only bulb 1 is out, only bulb 2 is out, both bulbs are out, or there is no problem. So we have to come back to our definitions of opens and shorts again to be able to utilize here. But we're going to say, what would the result be if the circuit were open at A? So if we had a break in the circuit here at A, all right, all of these bulbs, they just need power and ground to be able to light. And so if I had a break at A and I had an open circuit where it was broke, then would this bulb have power and ground? And the answer is no. It would have no power, but it still would have a path to ground. So this one has no power, but it has ground. This one has no power as well, but it has ground. So then in this case, both bulbs are out. So both are out. Then what would be the result if we had a short to ground at A? So if I had a short to ground, then that would mean that I have a path to ground there. So even though this switch is shown as open, the understanding is that it can close. All right? So this part I want you to understand. You may have heard somebody say before that electricity always takes the path of least resistance. So that's a partially true statement. So the truth of it is that more electricity will flow where there's less resistance. And so we see that in this diagram here, that there's lower resistance here than here, so more electricity or more amperage flows here than it does there. But if it were true that electricity just took the path of least resistance, then this bulb would light and that one would not, and that's not what happens, all right? Both of those bulbs light. This one just has more current flowing than that one. But if it were true that electricity just took the path of least resistance, then parallel circuits wouldn't work, and they do. So it's not true that it just takes the path of least resistance, but it is true that more electricity will flow where there is less resistance. And so, one of the things I want you to understand, a battery like this is likely rated for like 500 amps, all right? So, the resistance, we know these two bulbs have resistance. It doesn't say in the diagram what they are, but we can make it up. It can be whatever. We can say that this has 2 ohms and that one has 2 ohms, right? So the total resistance this way is 2 plus 2 or 4, right? But what is the resistance of this short here now? It's next to none, right? So what will happen in a short like this is that the majority of 500 amps is going to try to go here. Some of it will go here. Electricity moves at the speed of light. So some of it's still going to try to go here because this is now a parallel branch. But the majority is going to go here. And so in that case, there's a fuse right here. And if we give an average fuse rating, we say that it's, 10 amps or something, all right? So if we say that this is a 10 amp fuse, then all 500 amps, the majority of 500 is going to try to go here. Once it exceeds 10 amps, then we're going to blow that fuse. And once that fuse blows, now we have a open circuit. So in this case, then this bulb would have a path to ground but no power. And this one would have a path to ground but again no power because of our blown fuse. And so again, both are out. And then you probably want to make a note for yourself that we would have a blown fuse. You can tell what my handwriting is like, right? So it's not a whole lot better even with a pencil, to be honest. So now if we move on to our next one, so if we move on again to our next one on this exercise, and it says, what would be the result if we had a circuit open at B? So if we had a break in the circuit and it was open at B, then what do we have? So does this bulb have power and ground? This one would have a path to power, but it would have no ground. So this one's out. Then this one would have ground, but it would have no power. So this one doesn't light either. And so again, both are out. So BO in this context is going to mean both bulbs are out. So what would be the result if we had a short to ground at B? So if now we had a short to ground right here. So if we had a short to ground, then what do we have? So in this case, what we have is this bulb would still have power and ground. But this one would have ground and ground. And so bulb 1 would work, but bulb 2 was out. So we'd have bulb 2 is out. All right? So in addition to that, you guys saw if these were two identical bulbs, then this one would have 6 volts, this one would have 6 volts. But once we have a short to ground right there, then this one would get the full 12 volts. So not only did this one go out, but this one also got brighter. So then the next question is, what would be the result if we had an open at C? So if we had an open at C, an open circuit here, then this bulb would have power but no path to ground. This one would have a path back to power, but it would have no path to ground. So again, we would have both out. Then what would be the result if we grounded the ground? So if we ground the ground, no problem. So we would have no problem. That says no problem. All right? So everything is okay. That says no problem. All right. So, next one. Using the drawing above, answer the following question. So this one is now a parallel circuit, right? So we've got our parallel circuit on this page. This would be our parallel circuit. So what would be the result if the circuit were open at A? So if we had a break in the circuit right there, this parallel circuit, then we've got a break here. So does this bulb have power and ground? Nope. What does it have? It has a path to ground, but no path back to power. So this one, does it still have power and ground? We understand this switch can close. So this one is fine. So we have bulb 2 is out. All right. Then what would be the result if the circuit were shorted to ground at A? So if I had a short to ground at A, so I want to give you a chance to think about that. So if I had a short to ground at A, then again, we're going to say that this has 500 amps. And we've got ourselves a 10 amp fuse. Very big, A for amps. But we've got our 10 amp fuse there. And so, again, electricity, more electricity will want to flow where there's less resistance. So the vast majority of that 500 amps from this battery is going to want to go here. Some will go down this path, some will also get on this path, but the majority is going to go here. And once we exceed 10 amps, then we blow that fuse, and then both are out. Because we're going to have a blown fuse, right? So blown fuse. So then what would be the result if we had a circuit that were open at B? So if we had a circuit open at B, then at B we would, if we had an open circuit here. So if we got a break in the circuit there, I'll redraw my little amps guy. So if we had a break in the circuit there, then because these are independent and there's 12 volts still available to this guy still has power and ground, bulb 2 works, bulb 1 would be out. So bulb 1 is out. Then what would be the result if we had a short to ground at B? So if we have a short to ground right here at B, same thing, we end up with a blown fuse. Blown fuse. So then what would be the result if we had an open at C? So if you get a break in the circuit at C, then for C, then what would A have? Bulb 1. Bulb 1, would we still have power and ground? Yep. So bulb 1 would still have power and ground, so bulb 1 works, but bulb 2 is out. So what we would have is bulb 2 is out. All right. What would be the result if we had a short to ground at our ground? If you ground the ground, then we have no problem. No problem there. Then what would be the result if we had an open at D? So if you get a break in the circuit at D, then understand what D is. D is the path back for that bulb and the path back to the battery for that bulb. So this is common to both bulbs. And so in that case, if you have a break in the circuit at D, then both are out. Then what would be the result if we had a short to ground at D? So if we ground the ground, then we have no problem. There's a little scenario. So what would cause the following symptoms? So I want you to think about these. We have options of higher voltage, loose connection, high resistance, or an open. So if we had lights that were brighter than normal, based on what we've done today already even, if we had lights brighter than normal, higher voltage pushes more amps. We saw that that bulb is brighter on 12 volts than it is on 6 volts. Intermittent light operation means sometimes it works and sometimes it doesn't. Loose connection, high resistance, open. Loose connection makes sense for that. Then dim lights. High resistance, we also have addressed that with the tail lights. One's brighter than the other. No light operation, and open. One of the things before we move on I want to express to you is that hopefully you're picking up on the fact that blown fuses are caused by shorts. If I have a blown fuse in this diagram at all, then if that fuse is blown, then I have a short. And then we can have a short either in the wiring but only on the power side. You'll notice that shorts on the ground side don't cause any problems. That especially if it's grounded all the time like that. A ground on the ground side is not a problem. But if I have a short to ground on the power side, it blows the fuse. So if you have blown fuses, it's either a short to ground on the power side or a short in the load.